Then I'm going to go to something that's closely related to the sequence alignments, and those are then the phylogenetic trees, because maybe you don't want to look at all these amino acids individually, but you want to see how relationships are, or how close receptors group together, and what the relationships are between them based on your sequence alignment. So the first step again is the same. So you have to select what you want to compare. And in this case, I'm just gonna compare the whole aminergic family. And then the next one, I'm gonna add the opioids just to see where, if we take the opioid receptors and all the aminergic receptors, where these opioids would end up in relationship to the aminergics. So here we have all the aminergic receptors and the opioid receptors. And then we have the normal segment selection again. So also for the phylogenetic tool, you can indicate what the phylogenetic tree should highlight, if it's the similarity for the whole receptor sequence, or if it's just for one transmembrane helix, or a sub-selection, for example, just the 7 transmembrane bundle. So let's test just the 7 transmembrane bundle. So I'm going to select TM1, TM2, TM3, 4, 5, 6, 7. And then here at the selected segments at the bottom, we see that we have indeed TMs 1 to 7. Then the last option of the phylogenetic tree, and you don't have to change this, the default options are fine, but if you want to go in a bit more detail, you can also do additional evaluations of the sequence alignments and the distance calculations. But I'm going to leave it for now. So now it's creating this sequence alignment in the back, and then once it's ready, it starts clustering it, and then it draws this very nice phylogenetic tree. And of course, as you're now probably used to, the GPCRdb doesn't just give you a figure that you can download, but it's an interactive tree. So you can highlight very different options. So right now, for example, at the outer end of each receptor, we have information about G protein coupling, whereas on the inner side, we have information about the receptor family of each receptor. And this is something that you can change. So for example, if you don't want information on the outer marker, so the ones here, or just want to highlight something else, you can indicate that here. And the inner markers you can also change here. So let's see where the opioids exactly end up. So now in blue, we have the aminergic receptors, and we have in orange, the opioid receptors. And what is interesting is that from a ligand perspective, we see that there are some overlap between the opioids and the histamine receptors, and also some other aminergic GPCRs. But here we see that the histamine receptors group together, and also the muscarinic receptors, and together they form a branch with the opioid receptors actually. So there's already in the sequence, there's some information about this potential cross-reactivity. Some smaller tweaks that you can do is if you, for example, don't like the names of the UniProt, or are more accustomed to the guide to pharmacology or IUPAR naming, you can adjust the names here as well. And instead of using a circular dendrogram, you can also use the horizontal dendrograms if you're more accustomed to that. And here at the top, this might be a bit small, you can make it full screen and also download the results again. If now, for example, I'm interested in seeing what the results are of the sequence alignment of the muscarinics with the opioids, we can click here on the opioid branch and then add them to group 1, so that's protein set 1, and then do the same for the muscarinics, so then they're highlighted. And directly from here, we can click on this, and then it creates a sequence alignment and takes us back to the previous tool. You can also create a second set, and that would allow you to create the sequence signatures. And that's, again, what we'll be discussing next time. Okay, so now, instead of just looking at these graphs and numbers and things, I might want to be interested in the actual similarity matrix between the receptors. So that's what you can find here. Sorry, I was a bit quick. Under sequence comparison, we have the receptor similarity, and right under the phylogenetic trees, we have the similarity matrix. So here, I'm gonna just quickly select the opioid receptors and the aminergic receptors again. So now they're both selected, and then go to the next page. And then I'm gonna select, and here we again also have the segment selection. And I'm gonna select just the structurally conserved generic positions. Then it does the same thing, so it calculates an alignment, and then it compares the sequence identity and the sequence similarity for all the receptors against each other. So that way you might also be seeing some patterns. So the similarities, as is highlighted here, are shown here, and the identities are shown here. And that also makes sense because the identities are, of course, generally lower, the sequence identities, when you're comparing them, than the sequence similarities. And overall, if we see here that here at the bottom we have the opioid receptors, and overall we can see that there's clearly a brighter color for the aminergic receptors compared to the opioid receptors. So they definitely form a distinct subfamily. But now you also have the numbers and the representation. Then we have one more hybrid form of this, and that's actually doing a blast against using the GPCRdb alignment. So for example, if we do a blast, then we can select a reference here. So for example, we are using the mu opioid receptors. So we select the mu opioid receptor and then continue to the next step. We want to compare all the sequence positions of the mu opioid receptor to, and that's what we're showing in the next one, to what other receptors. So for example, just again, the aminergic receptors. So in that case, if you use this tool, we're actually comparing one receptor to a set of other receptors. And when we're going through this, it does not only calculate the sequence alignment, so the sequence alignment is actually more or less the same, but it also shows you for the mu receptor what the identity and similarity and the length of the sequence is compared to the mu opioid. So for example, the 5-HT. The serotonin 1B receptor has a 26% identity with the mu opioid receptor and almost a 50% similarity. So that way you can maybe do more advanced analyses of your sequences if you're looking for specific traits. Then one feature that's also quite often used is also actually a same type of approach, but then instead of using the GPCRdb alignment, people have a sequence that they, for example, do not know the function of, but they have an indication that it might be a GPCR. So for that one, we use the BLAST non-GPCRdb query. And then you can place your sequence in here that you're interested in or working with. So for example, I've searched here in UniProt for a predicted GPCR that we don't have in the GPCRdb. And I want to know more about this GPCR. What does it align with? So I'm going to take this FASTA file here with the sequence information, paste it in here, and then it can either search against all the sequences that we have in the GPCRdb or only the human sequences. Well, in this case, I'm just interested in any hits because it's a very unknown protein, so I'm happy with anything that I can get. So after this blast, you will get some hits and information. It actually gives you the results of the blast parsed. So it shows you the best results at the top, and actually the e-values are quite good. So actually we might get some real information out of this. And then if we scroll down, you can see that the blast query and the blast hit are shown here. And you see there's quite some similarities within the sequence. So based on this information, you can then start exploring what these specific receptors are. So for example, here we have of the clawed frog, the Xenopus laevis, we have the orexin-2 receptor, and also here of the spotted hyena, apparently also an orexin-2 receptor. So it's very possible and likely actually that this predicted GPCR and this putative GPCR might also have something to do with the orexin function. So that way you can also use the GPCRdb for unknown sequences, something that something novel that you're working with.